that communication systems form a vital element in the correct operation of a substation or generating station. Typically, communication systems are used, A, to transmit or receive operating signals from a remote location, for example, permissive tripping, B, to transfer or receive signals for protection equipment, that is, pilot protection, C, to transmit data to and from a remote location, and D, to permit direct telephone conversation between operating personnel. Depending upon the type of communication circuit, the transmitted signal may be DC or AC, or in some cases both AC and DC are required. In certain cases, radio, microwave systems, or fiber optics are used as the communication transmission medium, but more frequently, the messages will be transmitted by way of solid wire telephone conductors. In any substation installation, along with the high voltage cables, structures, transformers, and switchgear, we must also be aware of the small, low voltage telephone cables which are brought in by the telephone company for connection to the power company's communication equipment. Generally, telephone circuits are owned by the telephone company and leased by the power company. For convenience, throughout this tape, let us call the telephone company Telco. In some cases, a telephone pair may be run to connect directly with another substation. For example, in the case of pilot wire connection. But more frequently, the wire pairs are combined into cable, and these cables are run back to Telco's central office or exchange. Each telephone cable usually contains a large number of twisted pairs of conductors suitably insulated and covered by an outer metallic sheath which is grounded. An outer plastic layer is added for mechanical protection. The cables are sometimes routed underground, but more often they are run along distribution poles with the sheath being grounded at frequent intervals, say every 1,000 feet. Under normal operating conditions, the voltage between a communications channel conductor pair will be relatively low. That is 48 volts DC for an idle and or working telephone line. When ringing signals occur, a superimposed 90 volt 20 hertz signal will be present. On the face of it, you would not expect these low voltage telephone lines to be dangerous in any way. Indeed, this is one of the problems. The appearance of the circuits might easily lead to complacency by telephone or power company technicians working on wire-line connected terminal equipment. We all need to learn and remember that in practice, these telephone circuits may in fact be subject to very serious hazards when a fault occurs on the power system. This then is the subject of this video program. In this tape and the succeeding videotape, we should be looking at A, how dangerous high voltages can occur in telephone circuits, B, the various protection devices that can be installed, C, different types of protective schemes, and D, coordination between the power company and telephone company in order to determine the most suitable protection scheme for each installation. But you may well ask, if we are looking at the protection of telephone circuits, isn't this the problem of the telephone company? Why should the power company interfere or even be concerned? Well, the fact is both parties are highly involved. For one, the special protection is required mainly because of power system conditions, say a fault occurring on a power line. In this situation, both telco and power company personnel and equipment could be exposed to sudden, hazardous high voltages. Also, during such a fault, it is vital that the various communication channels remain intact so as to permit relaying functions and transfer tripping to take place. We certainly do not want the wire pairs to fail at this time. Obviously, good coordination between the two companies is absolutely vital. One obvious reason is that the telephone company personnel probably do not appreciate all of the problems facing the power engineer, and vice versa. Only by looking at each other's requirements and limitations can satisfactory protection be provided. And this is another good reason for paying attention to this videotape. But just what is it that we are protecting against? How can a fault on the high voltage power system spill over and cause damage to the low voltage telephone system? Well, there are basically two causes. One is ground potential rise, known as GPR, and the other is mutual induction between the power line and the telephone line. You'll remember that we briefly touched on these subjects in earlier tapes. Let's look at these items in more detail and see how they affect the telephone circuits. First, mutual coupling, which may be capacitive, direct contact, or magnetic. Capacitive effects are, in most cases, reduced by shielding around cables. Direct contact refers to the rare instance of direct contact being made between power line and telephone line conductors. Most of our problems stem from magnetic coupling, which induces longitudinal voltage rise. This occurs because the telephone cable usually runs along the same route as the power line, and it is quite close. Under normal operating circumstances, the effect of mutual induction is quite small. This is because the magnetic fields from the three-phase power lines tend to cancel each other out. However, in the case of a single-phase line, there will always be some mutual induction present, perhaps increasing the cable's sheath voltage. In normal operation, the induced voltage may be, say, 50 volts. As the sheath is grounded at several points, there will always be some current flow. When a power line fault occurs, say a single phase to ground, then high current flow will be concentrated in one phase conductor. The increased magnetic induction will cause a high voltage rise in the telephone conductors. This is known as common mode longitudinal induced voltage rise because it is the same in all conductors. The difference in potential between conductors does not change, but both will rise in relation to ground. Current flow through the sheath will increase greatly, causing damage to the cable if conditions persist. These are short duration surges, as power line faults are usually cleared in less than a quarter of a second. Even under non-fault conditions, high voltage surges can be induced into the telephone wires by transient disturbances on the high voltage power system. For example, 1. Operation of circuit breakers. 2. Switching shunt capacitors. 3. Flashover of lightning arresters. 4. Operation of high voltage disconnect switches. And 5. Opening or closing of ground switches. In the next segment, we'll be looking at different forms of protection which are provided on the telephone lines to protect against high voltage induction. Now, let's take a look at GPR, ground potential rise. As we all know, a substation or power station is constructed upon a grounded metallic grid, or ground mat, as it's called. This may actually extend for some distance outside the perimeter of the substation. All of the switchyard structures and equipment are connected to this common ground mat. This means that any difference in potential between these devices is restricted to very low values. Even during power system faults or lightning strokes, any ground potential difference between items of equipment will be quite small. This is obviously essential from a safety aspect. If a technician is working with his feet at one potential and his hands at another, the difference in voltage will cause current to flow through his body. The result could be disastrous. The ground mat is solidly anchored deep into the earth through a number of grounding rods. Now, let's see what happens under fault conditions, say a single line-to-ground fault on this distribution line. The fault is fed from the substation transformer. Fault current travels along the line through the fault down into the earth. From here, the current flows through the earth to the substation grounding mat. Actually, the current flows through the earth in many parallel paths, seeking the least resistance, usually deep down, not on the surface. Consequently, the circulating fault current enters the grounding mat from below and from all surrounding directions. The current then flows through the grounding mat and returns to the transformer via the grounded neutral. We have often looked at this circulation of fault current in other examples throughout this program. The actual magnitude of fault current flowing will depend upon the resistance of the fault itself and the parallel resistance of the various flow paths through the earth. The initial voltage transient also depends upon the precise point in the voltage sine wave at the incidence of the fault. The power system inductive reactance resistance characteristic, that is, the X over R ratio, is a factor in determining the rate of decay of this transient. You will remember that we discussed this subject in our earlier tape of fault characteristics. We can safely say that the fault current is usually in the order of several thousand amps, perhaps even as high as 50,000 amps. Even though the fault path resistance may be quite low, this very high current flow will produce a significant voltage difference. For example, a fault current of 5,000 amps passing through a resistive path of 1 ohm would produce a voltage difference of 5,000 volts. The consequence, then, is that as the fault current passes through the ground resistance, it produces a rise in potential at the substation local ground. This may be in the order of a few hundred up to thousands of volts above the potential at remote ground. While substation design attempts to minimize GPR, 15 kilovolt levels have been recorded. As we move out of the perimeter of the substation, the ground potential rise reduces until at a distance of, say, 2,000 feet, the earth is close to remote ground potential. This is known as the substation zone of influence. At the substation, all of the structures and equipment are connected to the grounding mat. And even with GPR, there should be no potential difference between the different devices. But there is an exception, and I won't give you 3 guesses. The exception is the communication wire pairs. Now, in this example, pairs are routed so that there is no mutual induction, even when there is a power line fault. So mutual induction can't be a problem, but the telephone cable sheath will be grounded at some remote location, probably the telephone company's central office. The voltage in the conductors, say 100 to 200 volts, will be in relation to that remote ground. Now you can see the problem. Under fault conditions, we have a potential difference between local ground and remote ground. When the telephone wires enter the substation, the local ground may be several hundred or perhaps thousands of volts higher than the voltage on the pair of telephone conductors. Remember, these conductors are capacitance coupled to the cable sheath, which itself is connected to remote ground. Imagine a technician with one hand on the locally grounded cabinet door and the other hand on an incoming telephone terminal which is grounded remotely. If the ground potential difference is high, the resulting flow of current through the technician's body could be lethal. I'm sure you can think of many other ways in which you could put yourself across local and remote ground when working on telephone circuits. So, safety of personnel is a vital issue in this problem. Over and above that, considerable damage can be caused to telephone facilities by ground potential difference during fault conditions. Flashover from telephone terminals to ground can occur. If local and remote grounds become connected through the cable sheath, the power line fault current may try to flow through the sheath. Whole sections of telephone cables, telco central office equipment, and substation communication equipment have been destroyed in this manner. In addition to this, if the telephone circuit is part of a pilot protection scheme, the relays may misoperate or even fail to operate at all, resulting perhaps in serious damage to major equipment. Clearly, the area around incoming telco cable and associated power company equipment can be dangerous under system fault conditions. It is not at all the simple low-voltage circuitry that it appears to be. For this reason, the associated panels are especially designed with safety in mind, and safety notices are posted. Rubber mats and rubber gloves may be required when working on this panel. It's clear that protection equipment must be provided to combat this problem of high voltage rise. Now at this time, let's take a break, and then we'll come back and look at some of these protective devices. For now, switch off the tape and review this material in your workbook. Let's begin our discussion of telephone line protection by looking at a standard entrance facility. By standard, we mean a telco cable entering a substation where GPR is less than 300 volts. Generally, this occurs in an urban area. This type of installation does not require any special high voltage protection, but it still needs some protection. As the telephone cables are led into the substation, the location of the junction between the telephone company and the power company must be clearly defined. This is the point where telco's cables are connected to the power company's communication cables. This demarcation point defines clearly the area of responsibility. On one side, the telco is responsible for operation and maintenance, while the power company is responsible for all activities on the station side. The actual physical location of the demarcation point varies from company to company, as well as substation to substation. It may be located inside the substation control house. An alternative would be a weatherproof cabinet just inside the substation fence. Yet again, the weatherproof cabinet may be placed outside the fence. The actual location is an important consideration as the telephone company technician needs to make the terminal connections at this point. Locating the demarcation interface, that is the telco-powerco junction outside the substation fence, eliminates the need for the telephone technician to enter and work inside the substation area. Often two terminals are located adjacently at this interface, one connected to the telco cable and the other to the power company's cable. The telco technician is usually responsible for connecting the jumpers between the two. Often, the power company runs its own entrance cable from the interface to the communications panel inside the substation. In many standard installations, that is of low voltage rise, the entrance cable sheath is connected directly to the substation ground. Now, please don't take this arrangement as the only standard. There are many other configurations, as we shall see later. As with all telephone circuits, the telephone company technician connects protective devices on its own side of the interface. The main concern is to protect the cable insulation from high voltage transients. The most simple protection uses some type of air gap device, which flashes over and discharges the high voltage to ground. A very simple type of air gap arrestor consists of two metallic electrodes. This type of protection was originally installed as lightning protection on open wire telephone circuits. The air gap may be fixed or adjustable in some cases. It's set to flash over at the desired level of overvoltage, which will protect cable insulation. The spark gap breakdown voltages operate within the range of 1,000 volts to 100,000 volts. However, with insulated telephone lines, a more common problem is that of induced longitudinal voltage rise. This is usually within the range of 500 to 1,000 volts. In order to protect these lower voltage levels, one of the most common devices installed by telephone companies is the carbon block protector. The air gap between the carbon electrodes is set so that flashover will occur at the desired voltage level. For example, a 3 mil gap will flash over at a surge peak of 600 volts or a DC voltage of 500 volts. A protector is located at each end of the telephone line, that is, telco's central office, and at the telco-powerco interface. In most installations, two carbon block protectors are required for each telephone pair, that is, one on each conductor. The reason for this is that longitudinal voltage rise due to induction takes place in both conductors. The objective is to discharge the high voltage to ground and so protect the insulation from damage. For lightning protection, which is of very short duration, this works quite well. But in the case of a ground fault on the power line, the high current flow across the arc may be sustained for, say, 10 cycles or more. In order to prevent damage to the communication pair under these circumstances, a fusible pellet is mounted across the air gap. In the case of a sustained fault, the fuse link melts, and this permits a spring-loaded contact to short the line to ground. Remember, this will probably occur on both conductors of the pair. This also short-circuits the transmitted signal to ground and effectively puts the telephone line out of service until the fusible element of the carbon block is replaced. This is a distinct disadvantage from the power company's point of view. If the communications circuit happens to be part of a relay protection scheme, the power line may well become unprotected just at the time when it is needed most. Also, by shorting the conductors to ground, we may be applying a GPR, which is several hundred volts above the remote ground potential at the telco central office. While the GPR associated with standard telephone line protection is relatively low, it may still cause high current to flow in the telephone line conductors and sheath. Carbon block protectors have been around for many years, and they do provide an inexpensive method of protection against high voltage. One problem is maintenance. The gap between the carbon electrodes is not hermetically sealed. Moisture and carbon dust, which is produced by repeated firings, make the firing voltage somewhat erratic. The firing level reduces with age and firing activity until it finally shorts out. Carbon blocks may require occasional replacement, particularly after operation. The carbon block protector is not commonly used by itself to protect pairs when expected GPR is above 1,000 volts. The consequent heavy current flow can cause serious damage or even destroy the device. Another problem is that repeated flashovers or arcing tends to reduce the breakdown voltage and may cause a complete short circuit to ground. Carbon block protectors are not recommended to be used by themselves, where the voltage rise may be greater than 1,000 volts, and never on critical protective relaying circuits, which demand uninterrupted service. A more reliable type of protection is provided by the gas tube protector. In this arrangement, the spark over electrodes are placed in a hermetically sealed tube. Instead of air, the insulating medium is an inert gas at low pressure. This type of protector has obvious advantages. As the unit is sealed, the insulating gas remains clean and cannot be contaminated by humidity or other undesirable elements. The flashover voltage is much more precise than with the carbon type protector and is effective at lower voltage levels. The unit is also self-restoring. That is, as soon as the overvoltage has reduced, the arc is interrupted and the line returns to service. Here we see two two-element gas discharge tubes connected between each line and ground. Another common type is the three-element shown here. One element is connected to ground and each of the other two elements is connected to one of the conductor pairs. As soon as one element flashes to ground, the second element will also fire. This arrangement makes sure that both conductors discharge to ground simultaneously. One problem is that most gas tubes are not fail-safe. That is, if the gas leaks out of the envelope, there's no indication until the tube fails to operate. Indeed, in this condition, the tube may not fire until the voltage has reached several thousand volts instead of a few hundred. In some cases, a backup is provided for gas tubes. Carbon block protectors are often used for this. In recent years, telephone companies have started to use a new type of protector, which is being developed to replace both carbon blocks and gas tubes. The new protectors are solid-state devices using semiconductors. You'll remember that we looked at the Zener diode and other voltage regulating devices in tape number 15 in this series. You may wish to take another look at that tape in order to refresh your memory. The solid-state protector operates by discharging the line voltage to ground when it exceeds a preset value. These units have advantages. For example, they are faster in operation and fire at a more precise voltage. They also require less maintenance. However, as with all of the other protectors that we have discussed so far, they by themselves do not provide satisfactory protection for voltage rises above 1,000 volts. All of these protection devices have one thing in common. They discharge the overvoltage by connecting it to ground and so converting it into a large current flow. This operation is often known as voltage clamping because we are, in effect, clamping the voltage to ground. Unfortunately, this has the effect of putting the communication line out of service until restored. Where uninterrupted communication is essential, another type of protector should be installed. This is the mutual drainage reactor. For direct drainage, it is connected like this. The two coil windings are mounted on a single magnetic core, and the center point is grounded. When the telephone line is operating under normal conditions, there is always a small AC voltage difference across the pair, causing current to flow. This could be, say, voice or audio data. The reactor is precisely wound so that under these conditions, each winding magnetizes the core in the same direction. As a result of this, the reactor presents a very high impedance to the flow of current to ground, and the communication signal passes with very little loss. However, if the voltage rises excessively due to longitudinal induction, the common mode voltage will now magnetize each side of the reactor in opposite directions. The essential feature of longitudinal induced voltage is that both of the telephone line conductors suffer voltage rise of the same magnitude and phase. The mutual drainage reactor makes use of this fact. This will cancel out the magnetic flux in the reactive core, with the result that the reactor now presents a very low impedance to ground. Any induced common mode voltage is continuously shunted to ground. But it is important to note that the communication signal continues with no interruption and little loss. In another arrangement, the connection to ground is made through a gas discharge tube. This eliminates any signal loss until the tube discharges to ground on overvoltage. Only the induced common mode voltage will be shunted to ground. Note, AC and DC communication signals are not interrupted during an overvoltage condition. On pilot wire protection circuits, the protector is normally located at each end of the telephone line or other remote drainage locations. Drainage reactors can be obtained with continuous drainage ratings up to 50 amps, and for applications where transient line voltages could be as high as 20,000 volts. Okay, so much for standard protection devices on standard communication circuits. We must now turn our attention to protection against high voltage rise due to GPR and induction. This is definitely non-standard. We'll be looking at these high voltage special protection devices in the next segment. For now, please switch off the tape and thoroughly review this material in your workbook. In the last segment, we looked at the conventional type of protection, which is provided by the telephone company on all telephone circuits. We noted that, in general, these devices alone do not provide satisfactory protection for voltage rises above 1,000 volts. But we have already seen that in many substations, voltage rises above this level can appear on the telephone system during fault conditions. For this type of installation, additional protection schemes have been developed. These are connected at the so-called high voltage interface. This is the point where the entrance cable is connected to the power company's communication circuits. In this arrangement, we have two cable junction locations. One outside at a distance of, say, 2,000 feet from the center of the substation's zone of influence. At this point, the ground potential rise under fault conditions will be much lower than inside the substation. This is often called the remote drainage location. At this location, the ground potential difference to central office remote ground may be reduced to a few hundred volts or less. It is considered safe when compared with thousands of volts inside the substation. In order to provide the lowest resistance ground possible at this location, grounding rods or buried wire are sunk deep into the earth, close to true ground. This is the location where the telco general use cable is connected to a dedicated cable which continues on to the power company. Normally, other telephone customers will be fed by the same general use cable as it continues along its route. The second junction, located at the substation, is the so-called high voltage interface. The telephone protection equipment located at this point is known as High Voltage Special Protection, HVSP. This is in addition to standard protection, which was discussed in the last segment. Special attention must be given to the telephone cable installation, which connects these two junctions. In most cases, this will be the dedicated entrance cable. It is essential that the integrity of the cable sheath be maintained right up to the high voltage interface, and this sheath must be grounded only at the remote drainage location. It must not be connected to the substation ground in any way. Also, the sheath must be completely insulated from earth or other grounds. In many installations, the dedicated cable is run underground in PVC conduit within the substation ground grid area and to a point 10 feet outside of the ground mat. Usually, the cable has a high dielectric outer insulation jacket and so provides further insulation from nearby grounded structures. We'll be looking at installation details more closely in the next tape. In some installations, the station side of the high voltage interface is connected by yet another telephone cable to a communication panel, which is sometimes called the network interface, located, say, in the control house. The objective here is to physically keep the communication circuits away from the high voltage special protection devices as a safety measure. The high voltage special protection, that is HVSP, may be installed, operated, and maintained by either the power company or the telephone company. Where the telephone company owns the HVSP equipment, the demarcation interface between telco and powerco will be located downstream of the high voltage interface. However, there are exceptions to these arrangements. Make sure that you're aware of the precise arrangements within your own company installations. Beware, there may not be the same arrangements at every substation or power station. We'll be looking at typical protection configurations and installations in the next tape. Regardless of ownership, the principles and rules are the same. The HVSP equipment is connected between the dedicated cable and the communication equipment. Often, mutual drainage reactors are installed in addition to HVSP equipment. We'll look at this in more detail when we discuss installation in the next tape. So let's now take a look at some of these HV special protection devices. One of the earlier but still important HVSP devices is the neutralizing transformer. The neutralizing transformer is designed specifically to compensate, that is, to neutralize the local ground potential rise at the substation. This is the three-winding type. The primary is connected between the local substation ground and remote telco ground. If the local ground potential rises due to a power line fault, then current will flow through the primary winding. This in turn will induce a voltage in each of the two secondary windings. Each of these two windings are then connected in series with one of the telephone pair conductors. The transformer ratio between primary and secondary windings is usually 1:1. Therefore, the magnitude of the secondary voltage is similar to that of the primary or the ground potential rise. The secondary windings are wound so that the induced secondary voltage raises the potential of the wire pair by an amount equal to the GPR. Thus, the protected cable pairs are at the same potential as the station ground, which has now increased by an amount equal to the GPR. In this way, the potential rise in both conductors due to GPR is neutralized. The voltage difference occurs across the transformer instead of at the cable termination. This prevents firing of the carbon blocks. The telephone pair continue to function as normal, with both AC and DC signals being allowed to pass. Neutralizing transformers are available to protect against GPR of 2,000 volts upwards, even as high as 25,000 volts. Often the neutralizing transformer has multiple secondary windings so that it can be connected into a number of conductor pairs. Neutralizing transformers are usually oil-filled. They are quite large and heavy and therefore expensive in relation to other protective devices. One serious problem with the neutralizing transformer is that it may lose some protection capability if it is subjected to rated voltage or higher. Also, it may become quite ineffective if the ground connection on either side is lost or its resistance increased. Some improvement in economy can be made by using a two-winding neutralizing transformer. In this case, the primary winding has been eliminated, and the unit is often referred to as a neutralizing reactor. Under normal operation, the low-voltage telephone signal is circulating through the pair of conductors in opposite directions, so the reactor core is not magnetized and impedance is low. However, if a local ground potential rise occurs, current will circulate to ground through the capacitance of the cable. Often additional capacitors are added, like this, to make sure that there is sufficient circulating current. The difference in voltage between local and remote ground causes current to flow up the station ground, through the capacitors at the station end, through each conductor, and back to ground via the cable capacitance at the remote end. As the difference in voltage may be as high as, say, 1,000 volts, the capacitive current flowing will be quite high. And note, it is flowing in the same direction through both of the reactor windings. In this case, the reactor core magnetizes strongly and so creates a high impedance to the flow of this current. In fact, the voltage difference now appears across the reactor. This is the same effect as the neutralizing transformer that we just studied. It retains the original potential relationship between the telephone pair and the local ground. In this arrangement, it is important to be aware that the capacitors must have sufficient voltage rating to withstand the maximum GPR anticipated. With this type of installation, it is necessary to check the capacitors frequently. Another type of high voltage protection for telephone lines is provided by isolation transformers. Basically, it is a two-winding transformer with high insulation characteristics. They are inserted into each wire line pair serving the substation. The objective is to isolate the connected station equipment, such as telemetering or SCADA, from the telco line, which is actually a source of remote ground. The isolation transformer is situated so as to keep any local ground potential rise isolated to everything that is bonded to the station ground grid. This eliminates the possibility of individuals or equipment getting across local and remote ground. A separate isolation transformer is required for each pair of conductors. They are manufactured with isolation ratings up to 20,000 volts and will function within the frequency range of 17 hertz to 1 megahertz. This allows the use of communication over carrier channels up to 24 per pair. Of course, any longitudinal induced voltage will not pass through the transformer, because remember, this voltage rise is the same on both conductors, that is, common mode. In many installations, isolation transformers are used as a combination drainage device. In this arrangement, the station side of the transformer is center tapped and grounded to serve as a drainage coil. These units are available with a draining current range from 1/4 amp all the way up to 100 amps. This type of protection is very satisfactory, except for the fact that it cannot be used where DC signals are required. As there is no metallic connection between the two sides, DC signals cannot pass through the transformer. This is an important limitation because DC as well as AC is necessary for many of our communication circuits. The most obvious case is the voice telephone circuit. Here, the voice signals are AC, usually AM, amplitude modulation, but the telephone operation and line control is performed by DC. For the sake of us non-telephone types, let's briefly review this. A 48-volt DC supply is applied across each pair of conductors at the central office. This 48-volt DC potential difference exists all the way along the line, right up to the telephone handset. Of course, there will be a small voltage loss when current starts to flow, and this happens when you lift the phone off the hook. This action places a resistor across the DC voltage and allows a current in milliamps to flow. When this signal reaches the telco central office, the line is connected into the exchange system so that you can make the call. Your line is now reserved and you will hear a dial tone. In telephone jargon, the line is now seized. When you dial the number on a rotary dial, DC pulses are transmitted along the line to the exchange. When you talk into the telephone, although the voice signal is AC, DC is needed to power the instrument transmitter and receiver. So from this little diversion, you can see that for voice telephone, both AC and DC signals must be allowed to flow through the high voltage protection. The same situation exists in any communication circuit where you need to seize a line before transmitting the message, data transfer by modem, for example. Various methods of transmitting both AC and DC are in use, and we'll be looking at these items later in this tape. Having said all of this, we have to point out that the isolating transformer can still be used as a high voltage protector for AC-DC application, provided special arrangements are made for the DC component. For telephone service wire lines, a special combination isolating transformer and relay is used. In this arrangement, the transformer operates as an isolating device only, and the high dielectric relay takes care of the telephone switch hook and dialing requirements, that is, the DC operation. The relay is energized from the station side, but its contact is connected on the telco side, hence the need for high 20 kilovolt insulation. On the substation side, the relay is energized from a local power source when the phone is lifted off the hook. This in turn closes the contact on the telco side and allows the 48-volt DC current to flow in the pair back to the central office to seize the line. For incoming calls, as the ringing signal is 20 hertz, 90 volts AC, which is passed by the isolating transformer, the relay is only needed to seize the line and stop the ringing signal. You'll find that lightning arresters and surge protection are connected, as is the case with all high voltage power equipment. The preferred type is the metal oxide gapless arrestor. The lightning arrestor is usually covered to protect personnel and equipment in case of an explosion. Even where cables are run underground, you will often find surge protection installed. The rating of these devices must be selected to match the insulation levels of the HVSP equipment. Safety has to be observed if any HVSP equipment is disconnected from service. It's unlikely that a fault and consequent GPR would occur at precisely that time, but it could happen. Whenever work is performed around HVSP equipment, safety precautions should be observed. Most utilities stipulate that appropriately rated rubber gloves must be worn when working on the circuit. As we mentioned before, some, but not all, power and telephone companies recommend thick rubber mats be used. Large warning signs are posted to indicate the potential danger. In recent times, optical isolators have begun to appear in high-voltage protection equipment. And we'll be taking a look at this in the next segment. For now, please switch off the tape and thoroughly review this material in your workbook. In the last segment, we talked about using isolating transformers so as to avoid metallic contact between incoming telephone conductors and the substation installation. In this manner, the two grounds, remote ground and local ground, are isolated from each other, and the problems associated with ground potential rise and longitudinal induced voltages are reduced. Another more modern method of doing this is to use an optical link between the two sides. As we know, the optical link transmits information over a beam of light and therefore provides extremely high isolation between the power company and telco facility. This method can protect against high GPR, at least up to any level which could be expected in a substation environment. Let's first take a look at the teleline isolator shown here. The principle is simple. For each channel, AC signals are passed through an isolating transformer, while DC is connected through an optical link. The cabinet is usually located at the high voltage interface. Inside the cabinet, the telephone cable pairs are brought along the bottom, and the station communications cable pairs are brought along the top. Between these two, there is an 8-inch air gap, which provides a high value of isolation. The optical link and associated isolating transformer is placed across the gap, so providing connection of the telephone circuits, but maintaining the high isolation value, about 18 kilovolts. The optical link is also known as the optical isolator. The link is in the form of cards containing printed circuit modules which are fitted into a rack like this. It is important to remember that the metal sheath of the incoming telephone cable is at remote ground potential. This must be connected to the insulated telco ground terminal in the cabinet. The upper ground terminal will be connected to the substation ground. So in effect, we have remote ground potential at the bottom of the cabinet and local ground potential at the top. The cable may contain several wire pairs. Each of these will be connected to a separate card. Each card has capacity for one 2-wire or 4-wire circuit. Each card contains the isolating transformers and optical isolators appropriate to that card's particular function. The electronics convert the DC signaling to AC tone frequencies above the audio band. These signals then pass through the optical converter for light transmission across the isolator. The optical signal, which is actually digital, is decoded at the receiving end and is converted back to an analog DC signal. The specific arrangement of each card varies depending upon the particular type of communication circuit. Individual cards are available for the following typical circuits: telephone, private or exchange line, private branch exchange, telegraph, data transmittal, pilot wire, telemetering and SCADA, DC trip, audio tone protective relaying. The pairs leaving the station side of the cabinet will be connected to their respective communication equipment, such as telephone, telemetering circuits, SCADA circuits, and protective relaying circuits. In order to make the fiber optic system work, DC power supplies are required for the electronics on both sides of the link. On the station side, this is provided from the power module, which can plug into the station 115-volt AC or station battery DC bus. Preferably, the supply should be uninterruptible. For the telco side of the link, the electronics are powered from the 48-volt DC on the line from the central office. In some earlier installations, power may be provided from the station side through the isolating transformer on each card. This combination of optical link and isolating transformer has considerable advantage over the older equipment that we discussed, such as neutralizing transformers. There is a great reduction in size and weight and consequently price. The cabinet is designed as an integrated protection unit, including surge protection. For maintenance, it's necessary to stock spare modules and carry out replacement in case of any defects. Another type of optical link protector is known as the Toucan system. In this case, we have two printed circuit boards located some distance apart. One terminal board is connected to the telephone system and the other to the substation communication interface. So we have one board at remote ground potential while the other is at substation local ground potential. The distance between the two boards is agreed between the two companies. It may be, say, 100 feet or even several miles in some cases, say at the remote drain point. At a minimum, the distance should be 5 feet, so as to eliminate the possibility of a technician getting his hands and feet across the two boards, that is, between local and remote ground. The two boards are connected by fiber optic cable, so providing the isolation link between the two systems. This could also provide the interface between the telephone company and power company. In this case, the station terminal board would be inside the substation perimeter, with the telco board located outside of the fence. The power supply for the telco board is taken from the telephone central office itself. This 48-volt or 24-volt DC is transmitted along the same conductors as the telephone communication. One word of caution. These conductors are usually quite small, say 22 gauge, and if the distance is long, the power supply voltage would suffer considerable voltage drop. It may be necessary to parallel other pairs of conductors in order to maintain the correct operating voltage, and this in turn adds to additional cost and maintenance requirements. The system permits the transfer of AC signal and DC signaling across the fiber cable. The telco side card converts the incoming communication signals to fiber optic signals. It works by converting the audio signal to a frequency modulated signal. This in turn drives a fiber optic transmitter, which puts a frequency modulated light beam over the fiber optic cable. One point of significance here is that the longer the optic cable, the weaker will be the receiving light beam. This system is rated for up to 2.2 miles of physical separation. A different carrier frequency is used in each direction, typically 85.8 kilohertz and 93.8 kilohertz. For DC transmission, the analog signal is converted to digital pulses, which in turn are linked via the light beam. This system allows for 2-wire or 4-wire communication. In most telephone systems, 2 wires are all that is required. We speak and listen at the same time over the same pair of wires. However, for transmission of data, 4-wire circuits are often used, that is, one pair of wires to transmit and the other pair to receive. For signals being received from the opposite direction, the unit transforms the optical signal to FM and in turn demodulates this to the audio signal, which is sent along the copper wires into the telephone system. A similar operation takes place at the substation connection board. In this case, the power supply is taken from the substation system itself. This may be DC or uninterruptible AC power. The card itself works on DC 24 volts. This card will supply enough current to power local telephones. The ringer supplies 90 volts to ring up to 5 phones in the substation. The voice, signaling, and ringing functions are all frequency modulated. You can see that this system has some obvious advantages, the main one being the virtually unlimited isolation. Each foot of fiber link provides 30 kV of isolation. Also, the size and weight of the connection cards at each end are exceedingly small, especially when compared with such equipment as neutralizing transformers. The cards are usually mounted in racks, which allow for multiple phone installations. As you can see, fiber optic systems allow a true physical separation of the power station ground grid and remote telco ground. In yet another fiber optic scheme, the fiber optic cable is run all the way from the telco central office to the substation. This system employs a signal multiplexer at each end, allowing up to 24 communication channels to transmit information. The time division multiplexer converts the signals to pulses of light for optic transmission. The signals are passed along 2 fibers, one to transmit and one to receive. In this system, there is no wire connection between telco and the power company, so eliminating any induced longitudinal voltage. Also, there is maximum possible isolation between ground potential at each end, so reducing or eliminating problems of GPR. As you would guess, this system is quite expensive and is not yet in widespread use. So in this tape, we've been looking at the problems and hazards associated with high voltage telephone circuits, which are located in and around substations and power stations. We also reviewed the various protection devices which are commonly installed. In the next tape, we'll continue this subject and examine in more detail specific protection schemes for different types of communication circuits. And then we'll go on to discuss installation techniques and inspection requirements. Please switch off the tape now and thoroughly review this material in your workbook.